Now we want to start taking a detailed look at linear transformations. A transformation is just a rule that assigns to each vector in the domain a vector in the codomain. So in this case, we'll start with a domain of Rn, and we'll have a codomain of Rm. So if x is in the domain of Rn, then t of x, the image of x under t, will be sitting in the codomain. We distinguish between the codomain and the range. The codomain is where the images are. The range is the set of all the images. Functions fit this description. So for example, the function f mapping the real numbers to the real numbers given by f of x equals x squared is transformation. The domain is going to be the real numbers. The codomain is also the real numbers. And the range for this function is non-negative real numbers. Because when we square a negative, we end up with a positive. When we square 0, we get 0. We know that f of 2 is equal to 4, so we could say that 4 is the image of 2 under f. So we're not looking at something new, we're just expanding on something old like we always do. This is just the idea of a transformation. A linear transformation is a transformation that respects scalar multiplication and vector addition. What that means is that a transformation is a linear transformation if the image of a scalar times a vector is that scalar times the image of the vector. And when we say that transformation respects vector addition, the image of a sum is the sum of the images. So those are the requirements to make a linear transformation. Why this is relevant to our interests and all our interest in matrices and linear systems and so on. A matrix multiplication always makes a linear transformations. Matrix transformations are always linear transformations. Let's look at an example where we define a linear transformation with matrix multiplication. So here's the example from Canvas. So T is going to map R2 to R3, and it's going to be given by the multiplication by the matrix A, a 3 by 2 matrix. So if I take something from the domain, some vector in R2, and multiply it by a 3 by 2 matrix, I'll end up with a 3 by 1 vector. So AX is only defined when A is 3 by 2. If X is 2 by 1, the inner ones have to match. The number of rows of X has to equal the number of columns of A, because we're going to be making a linear combination of the columns of A. And the result is going to be a linear combination of the columns of A. Since the columns of A are 3 by 1, AX will be 3 by 1. The inner ones have to match for the multiplication to be defined. The outer ones will tell you the size of the product. Let's just look at some examples. Let's suppose that U is the vector 2, 0, and V is the vector 3, negative 2. So a couple of vectors in R2, and we're going to apply the map and find out what their images are in R3. To do that, we just do multiplication. T of U is A times U. So here we are multiplying A times the vector 2, 0. So that means take 2 of the first column of A and 0 of the second column of A. We're looking at matrix multiplication and thinking of it in terms of linear combinations. So 2 times the first column of A plus 0 times the second column of A, and we get 2, negative 4, 6. We'll do the same thing with AV. We'll make a linear combination of the columns of A using the entries in V as weights. So I'm going to have 3 times the first column of A minus 2 times the second column of A, and so we get 7, negative 4, 5. We should verify that this matrix multiplication is going to respect vector addition and scalar multiplication. So if we just add the vectors U and V, we get 5, negative 2. And notice that if we do T of U plus V, I want to multiply A by 5, negative 2. I have 5 copies of the first column of A minus 2 copies of the second column of A. These 5 copies of the first column of A are 2 from AU and 3 from V. The negative 2 copies of the second column of A are 0 from the U and the negative 2 from the V. So since matrix multiplication respects vector addition, linear transformations will also respect vector addition. Also notice that if I take T of U plus T of V, we get 9, negative 8, 11. So from both directions. We get what we were looking for. We can do the same thing with 4 times the vector V. 4 times V is 12, negative 8. We make the combination, we get 28, negative 16, 20, and that's just 4 times T of V. This is just 4 times T of V. Note that this does not prove that T is a linear transformation. It does fit the description, but we can't prove something is true using examples. This helps us see that T might be linear, but it doesn't prove that T is linear. We don't get to prove things using examples. For example, I could come up with a theorem. All cars are blue in color. Proof: my car is blue in color. We can't use an example to prove something is true. No amount of examples will prove that this is true. I could find 1 million blue cars, and that does not prove that all cars are blue. Now, we can find a counterexample to disprove things. So we can disprove a statement with a counterexample. So if I make the theorem, all cars are blue in color, all you have to do is come up and say, false, my car is red in color. So counterexamples work for disproving things. They do not work for proving things. All right. In this case, we've started with a vector in the domain and found the image in the codomain. In math, we have to learn things forwards and backwards. So let's do the reverse. Still going to use the matrix A, but let's say P and Q are vectors in R3. So P is negative 9, negative 2, 5, and Q is negative 1, negative 3, 6. And let's suppose that we want to find x such that T of x is equal to P, and find another x such that T of x is equal to Q. T of x is the image of x under the transformation, and that's just multiplication by the matrix A. So we're taking this request in transformations and just turning it into a matrix equation that we have to solve. So we need to solve A, x equals P, and for that, we're going to go back all the way to the beginning to an augmented matrix. So we just drop our augmented matrix into our calculating machine. We look for it, there it is. We just drop our augmented matrix into our calculating machine, find the reduced echelon form. Remember, this is an augmented matrix. So we don't have x1, x2, and x3. We just have x1 and x2 in the coefficient matrix. And then this, the last column, negative 1, 4, and 0, the rightmost column of the augmented matrix is where we'll find the solutions. So x1 is equal to negative 1, x2 is equal to 4. So our solution, x is negative 1, 4. Here's the vector x such that T of x is equal to P. We want to do the same thing with Q. I'm just going to make another augmented matrix where A, and then the rightmost column will be Q. And here, when we find the reduced echelon form, we find a pivot in the rightmost column of an augmented matrix. So here's the matrix A, Q, an augmented matrix, and it has a pivot in the rightmost column. Therefore, the equation AX equals Q is inconsistent. Therefore, there is no x such that T of x equals Q. we could say that Q is not the image of any X under T. So Q is not the image of any X under T. We could also say this by saying Q is not in the range of T. Remember, we're making distinctions between comments about matrices, comments about equations, and comments about transformations. The augmented matrix has a pivot in the rightmost column. Therefore, the equation is inconsistent. Therefore, Q is not in the range of the transformation T. One quick DVD bonus material here. Notice that the row operations that transform 1, -2, 3, -2, 1, -1, 2 into 1, 0, 0, and 0, 1, 0. When I was solving AX equals P, I performed the same row operations as I was performing AX equals Q. So if we know we're going to be solving both of these equations, one thing we might want to do is just put both P and Q and just augment our augmented matrix. So if I make a matrix -1, -2, 3, -2, -1, 2, and I make an augmented matrix and put P in this column, -9, -2, 5. But then I realize I have to solve this another equation where I'm just going to replace all the rightmost column. I'm just going to make 2 rightmost columns. Make a super augmented matrix because the row operations are all going to come from these first 2 columns. So I'm going to put Q in kind of my extra augmented matrix. So I'm going to put A and not just put P in the rightmost column. I'm going to make another rightmost column with Q. Some kind of super augmented matrix. The row operations are the same in both augmented matrices. So if I find the reduced echelon form of this matrix, the first 3 columns will be the reduced echelon form of A, P, and then the first, second, and fourth columns will be the reduced echelon form of A, Q. So save myself a little bit of effort by solving 2 equations at once. So I have a reduced echelon form of 1, 0, 0, 0, 1, 0. The first rightmost column will be -1, 4, 0. And then the second rightmost column will be 0, 0, 1. So if you know you're going to be solving with the same set of row operations, just do all your operations at once. All right, let's pause the video here, and we'll do one more example where we talk about defining a linear transformation and finding a matrix that matches the description.